Swayam Prabha. Digital India. Educated India.
Okay, so 2D geometry again. The problem is kind of a so I have been trying to give to you some flavor of how randomness can be brought into algorithms. Here is one K or C disk, C, okay, C, let it be C. There is something like a UK US, no? I do not know which is what, anyway. So, I can even call it to be the smallest enclosing disk. So, the problem is as follows. Again, as always, you have a set of points only on the plane, n points in R2. So, let me make this distinction. I will call this, call this to be a circle, right. So, circle would essentially mean the boundary only, and if I consider its interior as well with the boundary, then I would call it to be the disk. Right. So, I interchangeably use terms, but essentially it is like the boundary and whatever is inside is the disk. So, our problem is given this n points on the plane, I want to find the smallest disk that encloses this set of points. Fine. That means this disk with the smallest radius that encloses this set of points. Is this the smallest disk? Yes? No? Maybe, let us see. Fine. Now, see, there are problems in geometry where it is like more of an aggregating property. But say for example, you want to compute the, so a very simple example is like you want to compute the centroid of a set of points, right. So, it is all points that you sum them and that is your centroid. So, centroid is kind of a function of all of the points in there, right. But you understand that properties like convex hull, minimum enclosing disk, say width of a set of points, these are kind of extremum properties which are essentially dominated by a few points, right. So, convex hull is dictated not by the points inside rather than the points outside. So, minimum enclosing disk is also probably would admit going to be a property like that, no, because 3 points uniquely define a circle, and can it be so that the minimum enclosing disk does not have any point from the set capital P on its boundary, right. Everyone should loudly say no. So, you need to have at least one point. Fine. So, that is our first observation about this problem. Let us gather observations. Now, see, to design good algorithms, essentially what you would always need to do is look at the problem and try to characterize it as best as you can. The better your characterization is, the better is your algorithm. Say for example, you take convex hull, right. So, what is the property of convex hull, or finding convex polytopes in any dimension? You are looking at a supporting hyperplane or a line on one side of which everything lies. Take any 2 points, and if it has many points on both its sides, then it is not going to be a supporting hyperplane or a supporting line of the convex hull, right. So, this is what I mean by characterizations of the problem. So, let us try to characterize this problem. First is, the first observation, as you said, is like I need to have this cannot be the scenario, right. At least this has to be the scenario. So, if I draw any roundish kind of object, assume that it is a circle. Okay. Have a circle in mind. Well, at least one point, but is that all? Minimum 2 points, okay. That is a good thing. You must be very good in your geometry, yes. So, what he is saying is our observation 2, what he says is on the minimum enclosing circle, there should be at least 2 points. He has said something more, let us try to figure that out. What he says is, he says that if you have 2 points on the boundary for a minimum enclosing disk, then they should be diametrically opposite. Why? So, say for example, this is the scenario where you have only 2 points that defines it. Then possibly what you can do is, you look at the line segment that joins these 2 points, right. Take the, it is a chord. So, if you take its perpendicular bisector, it should go through its, good, somewhere here. And then possibly what you can do is, you can push the center closer to this side, because see there is some leeway on this side, no, because you have said that it is not diametrically opposite, then there must be an arc of that subtends an angle more than pi, right. If it is not diametrically opposite, it should subtend at the center an angle, right, should subtend an angle more than pi. So, then what you can do is push the center a little bit on this side, so that this leeway is gone. So, you have a smaller circle, no? Fine. Okay. Maybe the smaller circle would look like this, something like this. So, if it is 2 points, it has to be diametrically opposite, first characterization, good. 1 point does not help. If 2 points define our minimum enclosing circle, then these 2 points have to be next. Okay, we obviously work with the assumption that, let us go back and start with the basic assumption that we make. What is the assumption? Right, no 4 points co-circular, no 4 or more points co-circular. That will make our lives a little easier. Let us look at our next observation. What is if it is 3 points? So, if it is 3 points, it defines a unique circle, fine, but the question is, can these 3 points be such that one of the arcs is more than pi? Again no, because of the same reason, right. The same argument, you can do a little bit of geometry to figure this out, that this cannot be the scenario of the minimum enclosing disk. Again you can play the same game. So, what we collect from here is taking all these observations together, the minimum enclosing disk is either going to be defined by two points of my point set P, say 2 points of P, name them say P and Q, such that P Q are diametrically opposite, or 3 points such that the greatest angle or arc subtended is less than pi. Fine. So, this is my characterization. Now, see, this characterization straight away gives me an algorithm. What I will do? I will take, first I will start with all pairs of points, NC too many pairs, put them diametrically opposite, form the circle equation is defined. I check it now against all other points, whether they are inside or not. So, settling this takes how much time? No, n square pairs, and for each one of them I have to check for linear number of inclusion or exclusion tests. So, n cube for this case number 1. For case number 2, I will need to look at NC 3 pairs, right, defines a unique circle, I test for inclusion or exclusion. So, this characterization, this simple characterization straight away gives me algorithm of order n to the power of 4, right, because NC 3 is order n cube and I test for all other n points, inclusion or exclusion, right. So, this is at least polynomially solvable, fine. Our goal is to bring this down to, how much do you want? Log n cannot be, right, it cannot be sublinear, no, you have to see at least read all the points. No, let us be ambitious, no. Well, if you are interested in n log n, think of this. I did not want to say that because I did not cover farthest point Voronoi diagram to a great extent, but as I was discussing about farthest, so take this as an exercise. You might do this. Solve the minimum enclosing circle using So, this Voronoi diagram we were discussing was this nearest neighbor Voronoi diagram. So, this is the furthest Now, what you first do is, so the idea would be first construct the Voronoi diagram, this farthest neighbor Voronoi diagram. The farthest neighbor Voronoi diagram, if you look at the nearest neighbor Voronoi diagram, its structure was some closed convex regions and outside for the convexal points open convex regions, right. But the farthest neighbor Voronoi diagram will have an interesting structure, it will be kind of a tree like structure. It cannot have a closed structure, no, because if it has a closed structure, think of this, I mean let us not talk of proofs, but think of this. If it has a closed structure, you have the point for which you are seeking the farthest neighbors, no. So, they would be coming off from a further region, not in a closed region, right. So, this tells you that the cells of the farthest neighbor Voronoi diagram are not going to be closed regions. So, that means that the edges of the farthest neighbor Voronoi diagram would not form a cycle kind of structure, there would be a tree kind of structure, right. And one can show that if you take the Voronoi vertices of the farthest neighbor Voronoi diagram and for each point, so what is the characterization of a point on the Voronoi diagram? You always know its farthest neighbor, right. So, one can show that your center of the minimum enclosing disk always lies on this edges or vertices of the farthest neighbor Voronoi diagram. Linear structure. So, n log n you construct, then you do a linear scan on this number of vertices and edges of this farthest neighbor Voronoi diagram, and for each point you know its farthest neighbor. So, a circle should starting from here at least enclose that point, no, and that you know. When you construct the structure, keep that tag. So, this way you can do it in n log n. So, think of this exercise. So, for that what you have to do is look at the characterization of the farthest neighbor Voronoi diagram and then just look at this Voronoi diagram to figure this out. So, I hope we can possibly do it in n log n, but we are a little bit more ambitious. Linear, and our framework again would be this. There is no AC, this central AC is not working, because it is pretty hot out here. Okay. So, the algorithm structure is very simple. What I do is, I start with 2 points, say. Fine. I start with 2 points, I form, keeping them on the diameter, I form a circle, fine. So, randomly permute the point set. So, you have this point set with you. So, this is a random permutation of the n points. Okay, so, for a notation, when I write this, it means the first I points of the randomly permuted set. Okay. So, what I do is I start with these 2 points and keeping them on the boundary, keeping them on the diametrically opposite, form a circle, right. Take the next point. Now, the inclusion test of a point inside a circle is constant, right. I just see the distance from the center and I can figure this out, fine. Okay. So, if it is going to lie inside, we are happy, right, and if this keeps happening, so till the nth point we are done. We expect this to happen quite a lot. Now, say the fourth point comes outside. Now, what do we do? Okay, so think of this general scenario. Let us think of this general scenario that I have Pi and I have been able to compute this, and say I have three points on the boundary that define Pi. No? So, these are the 3 points from Pi that has defined my minimum enclosing circle for Pi. Okay. So, this is my minimum enclosing circle for Pi. So, here was my set Pi. So, then the Pi plus 1th point comes. If it is inside, fine. Okay. So, I use another notation. So, di minus 1 is the minimum enclosing circle for Pi minus 1, and so di is minimum enclosing circle for Pi. No, it is as because I have used this notation, let me make this I minus 1, let me make this I minus 1, and let me make this Pi, fine. So, we are in a scenario where Pi does not belong to di minus 1. No? So, this is my di minus 1. So, the question is, or center and Pi. How does it work? You are saying from the center take a line to Pi, extend the line this side, no? So, you say that I take a point here and Pi, and then I with this two as diametrically opposite I draw a circle. Now, do not you think that it is going to be too big? Okay, first do you admit, right? It is going to be too big, no? Well, I have not discounted that, I have not said no to that, but this claim that Pi and this, it is like it is going to be too big. Okay, we will go one by one. Let us see. Yeah, next. Farthest pair. Farthest pair in this whole set capital Pi. Huh? Again, what is the guarantee that it is going to be minimum? Yes.
Draw a line from the center of the circle to that point.
Pi.
Yeah.
Okay.
And it will cut the circle at some point.
Yes.
At which point, intersection point, the closest point of the circle means out of this point, replace that point with the Pi.
It's complicated. You say center to Pi. Then okay.
And the closest of that intersection point means
Closest of this intersection point with
any out of these 3 points, like so close, nearest point of this.
so I take this point, this.
There is 3 arcs. There is 3 arcs
Before there were 3 arcs, okay.
arc. So,
This one was arc, this one was arc, this was another arc.
so each point cut the arc in 2 parts, all 3 arcs, and half they leave to section.
I am totally confused of what you are saying.
Fine. The intersection point is closest to out of these 3.
Hmm?
Hindi बोल
हिंदी में बोलना चाहते हैं, बोलिए, लेकिन मेरा हिंदी उतना अच्छा नहीं है. Sometimes I think that if I speak Bengali, you will understand better than my Hindi. Anyway, go ahead. सबको हिंदी समझता है ना? Okay, fine. बंगाली भी समझता है. तो मैं बंगाली में पढ़ा हूँ क्या? No. किसके? I mean, see, when you say closest, so make your references correct. Through? Okay. Closest through this point. इसमें से शॉर्टेस्ट आर्क को देखो. हाँ.
पहला पॉइंट आएगा उन 3 में से, उसको रिप्लेस कर देंगे Pi से. इस केस में नीचे वाला पॉइंट है, पीक वाले के नीचे वाला पॉइंट,
ये वाला
इसको रिप्लेस कर देंगे Pi से.
इसको रिप्लेस कर देंगे Pi से. So I take this and these 3 points and construct a circle. Okay. This is what you want, but you could have had a point here, no? So say your Pi minus 1 could have these red points, and still this Di minus 1 could have been correct, no? Right? So your algorithm fails, it excludes some point. So your method is not working, right? अरे भाई कुछ तो एक आइडिया बताओ. Antipodal pairs of what and what?
Because it ensures that all points are inside in that circle.
Then what is the guarantee that it's minimum? You have to ensure that minimum thing, no? Okay, so my claim is as follows, as you give up and I know what I am going to teach. See, I mean, I sort of expected the fast answer from you to be that draw the minimum enclosing circle with these 4 points, right. That was probably the easiest one. Again, you could come up with a counter example as I drew, that again you could have points outside. So, the only claim that we can make is the new minimum enclosing disk is going to have Pi on its boundary. That is the only claim we can make, nothing more. Okay? Let us prove that. So, we will make a geometric proof of this, fine. Now, for that first observe the following, that if you have two disks that intersects, say one with a radius of r1, the other with a radius of r2, and your r2 is greater than r1, because I am going to get to a situation, I mean remember, I mean see the radius of di should obviously be more than radius of di minus 1, right. So, that is given. Now, I see this situation, I intersect two disks, one of a bigger radius, the other of a smaller radius, and I look at this arc. My claim is you agree? Because if it is not, if it is more than pi, then you can have, right, in R1, because see that is the intersection part, mind you, this was the intersection part only. So, I am arguing only on this intersection part. So, if this intersection part was more than pi, then you could have, so it is like 2R2, no, within which you cannot have 2R1 on the boundary, agreed. So, this is the first thing. So, you can write a very formal proof of this. No one has any confusion with this one? No? Fine. Now, I map this scenario to make this my di and make this my di minus 1, okay, because di is going to be of a bigger radius than di minus 1, and assume for a contradiction that the point pi does not lie on the boundary of di. So, your point pi is here, not on the boundary. So, assume for a contradiction pi does not lie on the boundary of di. But then the 3 points that should define the boundary of di should come from pi minus 1 only, right, you agree? See, pi which is outside of this capital pi minus 1 is not defining your di. So, whatever di has to be defined, di has to be defined by 3 points, these 3 points has to come from, right, and it should lie on the boundary of, so they can be here. Right, they have to lie within di minus 1 and has to be on the boundary of di, and that is the only zone they can be. Now, look at this arc. This arc is more than pi and this violates our this condition, right. 3 points should be such that the largest angle subtended should be less than pi, but it violates this. So, I cannot have this positioning of pi, right. So, what I have proved is if at the I minus 1 instance I had a minimum enclosing disk and there was a point outside, then the new minimum enclosing disk, only thing that I can say about it is it will have that point on the boundary. Okay. Now, with any doubts till now? So, this characterization is just going to be important. Now, our algorithm starts this way. I randomly permute the point set, start with the first 2 points, right. I take the third point. If it lies inside, very good. If it lies outside, what I know is the minimum enclosing disk of these 3 points should have this point on the boundary. So, I am looking at a version of the original problem that I started with, but a constant version of it. What was my original problem? Give me the minimum enclosing circle. Now, the moment I have a point outside, my problem is give me the minimum enclosing disk, but I give you now a one more constant, that this point which lied outside is constant to lie on the boundary. Okay? So, I invoke that call. So, with this, so now think of your p I minus 1, you have grown up to this. So, for the first I minus 1 points, you have built a nice disk, this ith point comes. You know that this is going to lie on the boundary. So, you give a call to almost the same version of the problem, now with I points, but with the restriction that the pith point, this point pi should lie on the boundary. So, this is a new problem with the first I points, but the constant is the pi has to lie on the boundary. I again start the algorithm afresh, again take 2 points, keep doing, but the constant is this point has to lie on the boundary. Okay. Now, then again there might be a situation when I have a point outside. Now, if I have this situation, now I have 2 points constant to lie on the boundary. Again I invoke an algorithm, same recursion. Now, the restriction is minimum disk with 2 points constant on the boundary, same I points. Now, when I go to the third level, so the first level was just minimum enclosing disk, second level is minimum disk enclosing disk with 1 point constant on the boundary, next level is minimum disk with 2 points constant on the boundary. Now, while running this, if I encounter 1 point outside, what does it imply? 3 points constant to lie on the boundary, that defines a unique circle. I have got my circle, right. So, this is the algorithm. It basically works on a nested level of recursion. So, my first level of recursion is minimum disk with n points. I start my algorithm, take 2 points, construct the diameter, see the third point, inside fine. So, I keep going, I minus 1th point, I have the disk, I get a point outside, fine. I invoke minimum enclosing disk with 1 point constant. I keep doing on the same I points, right, 2 points outside. The moment the third point comes, perfectly okay. Now, see, invoke this idea. I'll possibly write this more formally, but try to think along with me. What is happening? So, the first level of recursion, which is working on this minimum enclosing disk for n points, there is a loop which is running, and at the ith instant it invoked a minimum enclosing disk with 1 point constant on the boundary with this I points with which it was called. So, again it is trying to form the minimum enclosing disk of this I points with the pith point constant to lie on the boundary. Keeps doing, suddenly it gets a point outside, then it invokes the same I points with 2 points constant on the boundary. Does, operates on this I set. The moment it gets 1 point outside, you invoke that lemma. So, you have 3 points constant, you form the minimum enclosing circle, your recursion comes back here, you have the correct. So, it winds, the recursion now winds up to come back here to having found the correct minimum enclosing disk till I points. Again you see the I plus 1th point here, again you keep doing the same.
For each of the iteration, this set of I points, we are actually randomizing it at every.
See, the randomization is like over the input. So, what you can do is possibly you take the first set of I points, first set of n points, randomly permute, and then this capital Pi is defined for you. You go there, again you randomly permute there the first I points.
When I find a new set of I points,
No, you are operating on this Pi.
So that PI, that permutation is constant now.
See, it would even work if you work with, see, the set remains the same.
Set remains
Same.
For the ordering also.
Ordering you can work with a new permutation. It would even work if you have a random permutation at the beginning, right, and then you are working. So, you ith point comes, you have the set this capital P sub I, with that you have called the second level of recursion. Then what you can do is,
So here, whenever we are going to second level of recursion, so the permutation order remains same.
you can repermute, that's not a problem, you can repermute, but again you see, I mean, what you are going to do, this I points that you had obtained was a random permutation of your original set. So, even if you work with this set, this is going to be a random permutation of your original set. So, it would even work if you have a randomization at the very beginning and then keep working. But if you so like, you randomize at random. So, the set remains the same. Remember this, my first invocation was with n points. I was running a loop at the ith point. When I had considered the ith point, I had obtained the minimum enclosing disk di minus 1, Pi lied outside. That moment I invoke minimum disk function constant with 1 point on the boundary. What is the set? This capital P sub I, right. So, now I start my algorithm in the second level with P sub I, capital P sub I, and the small Pi constant to lie on the boundary, fine. Let me write it, I think that way you would appreciate better. So, this is my first level of recursion, minimum enclosing disk with the point set P. So, there what you do is your first step is randomly permute, then you have a loop, so if Pi belongs to di minus 1, then your di is equals to di minus 1, it remains same, else what you do is call min disk 1 with Pi and small p. Running over n on p, for loop is running okay. So, now you call min disk with capital Pi, and what is the point constant to lie on the boundary, that is small Pi. So, your min disk 1 is now some p and some small p, right. Again you can think of randomly permute p, then blah blah blah, do the same thing. Now, the main block is this one, no, because of the earlier claim. This block in here is just the same, but for this else call, it is a call with min disk 2 capital P, the small p and a q, right. So, if there was this for loop, and if your q belongs to this di minus 1, or just name it as some other disk, as because it is in here I minus 1, then di minus 1 dashed is same as, or rather the other way around, is same as this, else what happens? See, this function was putting small p. So, that means putting, this was the parameter that went into this one. So, this p is already constant to lie on the boundary, and now q is also outside. So, q is also now constant to lie on the boundary because of our earlier claim. So, this calls a different routine, right. Here there are 2 points constant.
But the time when the ball is made, so the circle size, the boundary is also growing, right? The boundary size is also growing by that.
Why it should grow?
Because if
Capital Pi, in whichever way it might come, its minimum enclosing disk should be the same, no? The order does not matter. The order matters for the time that you take to compute. See, if you have, consider this capital Pi and any permuted order of this capital Pi, your minimum enclosing disk should be the same, no? Right?
so we keep on doing until you get at 3 points and the
Right, that is it. So, again the same thing. So, in here also again the same block you carry over, but here the moment this else thing comes, then you know you have got 3 precise points that define di. Now, your recursion winds back here, winds back here. So, now you know, so the moment you have come back here, you have the correct smallest enclosing disk till I points. Again your loop here continues, again if you have a point outside, keep doing.
When you are calling the function read disk 1, so you are passing two parameters pi, the capital Pi and small pi.
Yeah.
What's this do?
You are not from a computer science background, no? So, see, look at this call. What is the parameter that I am passing? The parameter that I am passing is this, right, and the point is small pi. So, capital Pi is this p, right, and small pi is this p, is a point. I defined it earlier, no, was the set of the first I points. Right. Okay. So, the moment this algorithm, this this recursion, so there would be many multiple calls to this recursive functions, and the moment I finish this one, I come out of this main program, then because of the earlier claim I have got the correct minimum enclosing disk. Now, what remains is to analyze this. Now, you can analyze this in the following way. See, in the worst case what might happen? At each instance you are outside, right. So, the worst case happens, how much time should you take? Should be sum of I, no? So, roughly n square. Now, think of this, and this is the beauty of this extent measures. At any instance, you look at this capital Pi. Look at this capital Pi. Now, you obviously understand that whatever permutation that you take of Pi, di is the same, it is independent of the permutation, right. Now, what does that mean? And this is the beauty of the extent measures. So, there must be 3 points in this set which defines Pi, fine, which defines capital Di. Now, think of this situation. Yes, we have said 2. I am operating on the worst case. No? So, think of this situation where you have this 3 points appearing at the very beginning. No updations, no? Just carry over through. The minimum disk remains the same. This is the beauty of the extent measures. Okay? Now, think of this recursive thing. Just look at one level, you can carry over this argument to the other levels. Think of the invocation here, say maybe, and let us see how many times this invocation, how many times this is going to take, okay. Or even you can look at this. So, see, I am operating on the set capital Pi, and you have already agreed to this fact that the Di corresponding to Pi is defined only by 3 points. So, of them small Pi is 1, this I should have written this as, fine, let me write this as a Qi, right. So, of them Pi is 1, Qi is 1, and the other comes from the third invocation, fine. Now, look at say this level. So, you have already fixed 2 points, right. Now, think of this backward analysis. What does backward analysis tell you? That you are looking at a randomly permuted set, and as I was telling you at the very beginning, it would have been very messy if you calculated it this way, that I look at all random permutations, argue over each one of them, right. So, the essential idea was I condition on one permutation, right. And then I saw that we argued this one, right, that if you define capital Pi, whichever random permutation you take, capital Di is same. That property of the geometric structure remains invariant. The order does not matter. So, I can sort of get rid of this conditioning, and then I can just look at the last inserted point. If I take that randomly, that works, and that is what backward analysis is all about, right. Remember, this Pi was the last point inserted where it violated and was outside, right. Okay. Now, I know there are 3 points only that define, 2 have been already defined for me. There is now only one favorable case out of the I, or maybe I minus 2, which is going to damage you, but the probability of that is very low, no? Favorable to damage, I say. Fine. So, so this is called numerator, no? Yes, the upper thing is numerator. So, in the numerator it is 1, in the denominator it is I, right. So, your worst case happens if the last point is outside, and that can happen with a, it is your favorable case for this damaging thing is 1 and below you have I. So, in all now you take order n for this one, right. This is kind of a order n structure thing, because I am taking point by point and then I am calling that one, fine. So, in all I take an order n plus some amount of work I with a probability of some, sorry, I was going to rub it with my hands. So, it is the work taken is, I should put this inside, this is the amount of work that you do with a probability of constant. I am writing big O of 1 because if I look at this invocation it is 1, if I look at this invocation it is 2 points. So, essentially this cancels out and this runs from 1 to n. So, you have in all order n. So, this is the expected time that you take. So, the essential idea is, and this kind of argument, this kind of backward analysis argument sort of works through in different scenarios where this extremum kind of structure you are looking at, and there are only a few points that is going to define your structure. So, you have essentially got to get into that geometry a little bit and just figure this out. Yeah, I am doing an expectation calculation. So, that is the probability one, order 1 by I. So, you do this calculation over 2 levels essentially. So, you do over this level once, then you do over this level once. But again they are all, in one case it is 1, the other case it is 2. So, that is why I wrote big O of 1, and for the other, but there is always a loop in the other thing, no. But mind you that, so when you are invoking this, say for example you see here, so there is an order n, there is an order n because of this running, no, this running is order n, but this running is invoking a recursion not many times, but if it is invoking that recursion it is going to take I amount of time, because the cardinality of the set that you send to that level recursion is of I, size I, but in that the argument is, in that this amount of work is not done always, is only done for these cases, right. So, that amount of work you are not doing many times, that is the argument. So, I would finish by giving you some idea about one more problem that exactly fits in this framework and would, I think, would be taken up by someone in the next week, but even it is like Arijit was talking of this convex polytopes and stuff. So, how many of you are conversant with linear programming? 1, 2, 3, okay. So, what is about linear programming? What do you do? Say minimize a function over a certain domain, right, subject to a bunch of constants, and let these constants be some gx, gix of and let this be some bi's, and obviously you these are all vectors maybe, yeah, and you say that they are positive, right, and it is an LP if all these functions are linear functions, right. Now, think just 2D. So, think that all these functions are on the plane, fine. So, what will you have? Corresponding to each such linear function in the 2D, corresponding to each such function you will have a line and a side of the, so it sort of have corresponding to each constant hyperplanes, open on one side the feasible region, the other is infeasible. So, each one gives you such a convex set, no. So, each line gives you a convex set like this. So, basically the say the domain on which you operate is the intersection of all such feasible regions, each one is convex, and Origin has already said that the intersection of convex sets is convex. Okay. So, this one is going to give you a convex set, but it is not always going to be nice closed like this. It can be open, it can be empty, but again they are convex sets. Now, what you do is, so what you are now trying? You are trying to minimize this function over this region, and one can show that as because these are linear and convex functions, these extremum values will appear only at any one of these corners. Now, see this you can see as a function like this, sorry. Fine. So, essentially if you take this out, yeah. So, just look at this as a vector. You have all these coefficients of that linear function. So, that would essentially give you a vector. So, you are essentially looking at the extremum point inside this convex region in the direction of that vector, right. So, what you do is take that vector and sort of move a line parallel to it, and sooner or later you will hit the extremum point. So, this is kind of a very hand weaving argument, but you can put this in a much more mathematical framework to show that essentially all the corners of this convex region competes for the extremum value. Fine. Okay. Now, what you can possibly do is rotate these functions a little bit such that, so that will make life easier for us, such that always. So, if you are seeking the minimum, you should sort of reinterpret this problem in this way. You can rotate this vector, right, rotate this vector down. So, you are seeking essentially the bottommost point, no, because we told you that extremum point in the direction of the vector. So, now you have a geometric problem for your LP. You look at each line, you are going to from this convex region and going to find out its.
Understand why the extremum point is in the direction of the vector. But I am not clear.
Okay, we will do this while having tea. Okay. Okay, let's put it this way. Consider a maximization function, right? You can obviously obtain you can take a negative sign and work along for the. So, think of a maximization function. Fine, you are maximizing f x. So, then take this vector, consider a line which is perpendicular to this vector, right. Then if you move the vector a little bit away from this, do not you think that the function will increase, right? Keep doing this till you are in the convex region, it keeps increasing, no. So, the moment you hit a corner, if you just continue further, no, then it is infeasible region, no. So, that means a corner would give you the, right. So, now if you are seeing minimum, just take the negative and argue properly. Anyway, so this is about getting the minimum point. I am sort of giving you just some idea. So, again here you see what you can do is randomly permute these lines, okay. Randomly permute this line and keep computing. So, this is your situation, say till so like what was capital Pi there, say is capital Hi here, the first I lines. So, you will get a bottommost point. You introduce the I plus 1th line. If it is below, then it is a nice situation for us, right. The bottommost point till now survives, again the same case as inside the circle or outside the circle. If it is, see, if it is this side, then already it is an infeasible thing. No? The problem comes, this happens, then no longer this point would qualify as the minimum point, you will have to have a new minimum point. But because of convexity and linearity, you can argue that this new minimum point will lie only on this line, like you had argued there that the point outside should lie defined be on the boundary of di. Now see, it is a easy problem. I started to solve a 2-dimensional LP problem. Now it boils down to solving an 1-dimensional LP problem, where I know that my new minimum is constant to lie on this. What I do for the other h minus, for the other hi lines, I intersect it with this line. So, I intersect with this line and I have this regions, right. So, on each line, on this line intersected with each one of these lines in capital Hi, I have a region, right, on this line, agreed. I am working under the constant that the new minimum will lie on this line hi plus 1, small hi plus 1. So, what I do is, from the left I take the rightmost point, from the right I take the leftmost point, any two would qualify for the minimum, I check there. Again see, it is going to be only 2 points, again you can argue like this case. Again only there is only 2 lines. So, this is going to be changed only if you had, right. So, again you can make this same kind of argument. So, again you can have linear solving of this, but this does not naturally generalize to higher dimensions. Then you have a factorial in D. So, that is why, I mean, if you are solving LPs in low dimensions, this works, but do not try to use this if you are working for higher dimensions. I think this will be covered in much detail sometime later in the next week. I think we wind up.